Okay, so hello guys. This video and a series of 2 or 3 next videos, I'm trying to teach the whole of P3 calculus. The P3 calculus is relatively simple, so it's much easier than P4 calculus. So I believe I can teach it in around 30-40 minutes, and yeah, at least what you'll get from 30-40 minutes is basic stuff that's very good for you to start learning it with the teacher next. And don't worry, I have the textbook next to me. I'm teaching right according to the specification. It's exactly what the specification needs you. So in the textbook, differentiation starts with differentiating sine x and cosine x. So these are just some basic definitions that you'll have to learn. Y is equals to sine x. Don't forget, differentiating means finding the gradient function. The derivative is the function that gives you the gradient of a graph at a certain point, at a certain x value. So sine x looks like that, and y is equals to cosine x. This looks like this, right? Yeah. So dy dx of sine x, this is just a basic definition you need to learn. The proof is actually very complex, so you don't need to know that. The derivative of sine x is just cosine x. This is just a simple definition you need to know. And the derivative of cosine x is negative sine of x. So yeah, the gradient function of sine x is cosine x. The gradient function of cosine x is negative sine x. Now, a tip to help you remember the positive here and the negative here better so that you don't confuse them. Just look at the sketches of the respective graphs from point 0. So sine x, after starting from 0, is positive, isn't it? That's a positive line. That's a positive gradient. Hence, its gradient function is positive cosine x. And the graph of cosine x starts negatively initially from the point 0. So after 0, it has a negative gradient. Hence, the derivative of it is negative sine x. So when you differentiate, just know it becomes the other important trigonometric function from sine to cosine, cosine to sine. And for the sine, the plus or minus, remember to sketch and just look at the graph right after 0. It'll give you a hint, because for sine positive, cosine negative. So two very basic definitions. Once you've got this on your fingertips, you won't even have to remember them. It'll just be part of your muscle memory. So that's the first part of it done. And then next thing, now we go to differentiating exponentials and logarithms. Logarithms, don't be scared, they just want log to base e. So that's just learn, not log to base 10 or any other base. You don't need to know that. You just need to know differentiating log to base e, which is just learn. So, okay, if y is e raised to x, then its derivative just happens to be ex also. So this is actually one of the special things about the number e. You guys might be wondering, why were we taught the number e? The special thing is its function, its exponential function e raised to x, its derivative is exactly the same as the function. So if you sketch the graph, it looks like this, doesn't it? So at every value of x, the y value you get, at every value of x, the y value you get is also the gradient value at that point. So that's the special thing about the ex graph. So its derivative is just e raised to x. And for ln x, for y is equals to ln x. Remember, ln is just the same as writing log base ex. But now you should, now the standard notation is to write it as ln x. So the derivative of this is just, by standard definition, 1 over x. So these are some standard definitions. They're not really hard to learn. Once you've gotten used to them, again, it'll be part of your muscle memory. So that's all. That's it for standard definitions. Now we go to the important part, the big bad boy, chain rule. Chain rule is one of the most important tools you use in differentiating. So chain rule is for composite functions. You've learned composite functions in P3 chapter 2 or something, yeah? Composite functions is when you have a function inside of another function. It's not functions multiplying. That's a different thing. We'll get to that later. It's when there's a function inside another function. Composite functions. You remember f g of x, where you apply g first and then you apply f first. This is a composite function when we use chain rule here. Chain rule can be used for when there's, let's say, 4 functions all inside each other. So this inside this, inside this, inside this. But for P3 specification, you just need to know 2 functions like this. So just 2 functions working compositely. You need to know chain rule just for those, not anything more advanced. So chain rule now applies to all the basic definitions I've shown before, and when you have a binomial brackets, when a certain brackets is raised to a large power. So let's say chain rule. Let me show you what chain rule is. Let's say you have 2x plus 5 all raised to 4. Now if you were to open these brackets by multiplying the brackets 4 times, that will take you very long. So that's why chain rule exists, because this is a function inside of another function. The inside function is 2x plus 5, and the outside function, the whole thing being raised to 4. The outside function is x raised to 4. You can think of this x as being this whole thing. So 2x plus 5 is the small inside function, and the whole thing being raised to 4 is like the outside function. So how do you differentiate this? So I saw another video where they give an analogy of an onion. You peel layers from outside. An onion is arranged in layers from outside to inside. So that's how you use chain rule. You differentiate the outside function first, keeping everything what's inside the same, and then you differentiate the inside function and multiply the derivative of the inside function with the derivative of the outside function. And when you're differentiating the outside function, you're keeping all the things inside the same. So what does this mean? Let's say this is y. So dy dx will be, first we treat the outside function, which is just power of 4 being raising to the whole brackets. So that by normal differentiation becomes 4. Keep everything that's inside the same without touching it to the 3. You get that, yeah? 4 times 1, so 4, all raised to the same brackets. You keep it as the same, and then you subtract 1 from the power, you make it 3, times the derivative of the inside function. The inside function is 2x plus 5. You differentiate that, you get 2. So the overall derivative is 8, 2x plus 5, all raised to 3. So we did the outside function first, which is 1 times 4. The whole thing remains because we are differentiating the outside part first. We aren't touching the inside part. And then subtract 1 from the power. 4 minus 1, you get 3. And then multiply by the derivative of the inside function, you get that. So another example of this, say something very similar. Or we will, okay, y is equals to, let's say, 4x squared plus 7 all raised to 10. Again, opening these brackets would take you very long, and you would never do that in real life. So to differentiate this, let's put a 1 there. Of course there is. So we first work with the outside function, treating the whole of this as one large x, or we can write it as that if it makes it simpler. We treat the whole of that as one large x. So first differentiating the outside function, 1 times 10, 10 raised to capital X, all raised to 9, times the derivative of inside function is 4 times 2, 8x. Now remember, we treated this large x to be this whole brackets. So 10, 4x squared plus 7, all raised to 9 times 8x, which would be 80x into this. So you don't have to treat this whole thing as one large x. That was just that was just to show you that the inside function, at first we retain it, we don't change it in the beginning. So we just work with the outside one. 10 times 1, 10, all into retain the whole thing, 4x squared plus 7 raised to 10 minus 9. Remember, you subtract a power when you're differentiating. 10 minus 9 times 4 times 2, 8x. This gives 80x, 4x squared plus 7 all raised to 9. So that's it for chain rule. When this is called a binomial expansion, you don't need to expand it when certain terms in a brackets is being raised to power. So for binomial expansion, that's how you use the chain rule. Now, chain rule also comes when all the other things, all the other basic definitions I've already said. Because even then, let's say we have an example. If y is equals to sine of 2x. Now, why do you think this is chain rule? Because it's a function of a function. The inside function is 2x. The outside function is signing or sine of the whole thing. So outside function, inside function. again, chain rule comes here. We differentiate the outside function, keeping the inside the same, and then we differentiate the inside function and multiply. So sine of 2x. To differentiate this, the outside function is sine, remember? So we already know by definition that one becomes cosine, positive cosine. So cosine 2x, the inside function remains the same, times, no, this is the whole thing, times the derivative of the inside function is just 2, cos 2x, 2. So this gives 2 cos 2x. Again, this was just chain rule. If we had, say, y of cosine 7x, dy dx would be the derivative of just the outside part, cosine, becomes negative sine. That was from definition, I introduced with that. And then 7x remains, the inside function remains when you're differentiating the outside first. And then times 7 because, times 7 because that's the derivative of the inside function. Remember, this 7 is multiplying the whole of this. It's not negative sine of 49x. It's negative 7 sine of 7x, like that. So this 7 is multiplying the whole of this. Yeah, not this. That just could be a misconception. Not this, the other way. So that's the answer. So this is how chain rule applies to brackets, sine, cos, even e. Even when I said e raised to x. So y is e raised to, let's say, 4x. dy dx would be, the outside function is e. The outside function is e raised to something. So as we have already established, that remains the same. E raised to 4x times the derivative of the inside function, 4. So 4e 4x. That's all. So the exponential remains, because that was again a definition, ex differentiated remains ex. So e4x remains e4x times 4, which is the differential of the inside function. So that's e. And then even ln. Even, let's say you have y is ln of 2x. dy dx would be 1 over 2x times 2, which is okay, this is a special case, 1 over 2x, because first we differentiate the outside function ln, which makes you do 1 over something, and then derivative of inside is 2. This is a special case. Usually in this case it always comes out to 1 over x, but don't generalize. Chain rule can be used everywhere. So to summarize, chain rule can be used bracket when you have let me use binomial to make it easier, although it's not exactly that. Binomial cases is when, say, you have 2x plus 4 raised to 14, any power like that. So in such a case you use chain rule. Sine and cos when it's not just sine of x, when it's not just sine of x and cosine of x, when it is, say, sine of 4x, or it could even be cosine of 4x squared. In this case it should be negative sine, outside function, inside remains the same, 4x squared, then you multiply by the derivative of the inside, 4 times 2, 8x. So in such cases where it's not just plain sine of x and cosine of x, you have to use chain rule to differentiate the outside one, which is sine and cos, and then the inside one later, and multiply that. And then case number 3 for this is e raised to kx. E raised to x, e raised to just x, the derivative of this is just e raised to x. But when there's a k constant, the k will come out here, so it will become ke kx. Because k is a constant, so the derivative of kx is just k, so it will multiply with that. Yeah, you get it. And for ln, and also for ln. So basically, chain rule, a general rule, is composite functions, function inside of another function inside another function. An analogy is like peeling an onion. It's in layers. You start from outside, go inside. So first differentiate outside function, keeping the inside function the same, keeping inside function the same, and then differentiate inside function and multiply. So there you go, that's chain rule for you. It's something that if you practice, it'll get very easier. It's actually very beautiful. It's one of the best tools in a mathematician's toolbox, because differentiating complex functions gets hard, but when you use chain rule, it becomes easier. Oh, another example, let's say, so chain rule will work all cases. So let's say we have sine power 4x. Remember, this means sine of x whole thing to the fourth power. Now again, you see it's a function inside of another function. The inside function is sine, and the outside function is raising a whole bracket to 4. So dy dx is keeping the inside function the same, 4 sine of x, remove one power, 4 minus 1, so 3, and then times the derivative of the inside function, cosine x. So we get 4 cosine x sine cubed of x. And there you go, that's the derivative. By chain rule, you differentiate the outside first, keeping the inside the same, then you differentiate the inside and multiply. So in general, the textbook gives some general formulas or some general results. I just say them, but not really important. But let's say the textbook says for y is equals to f of x, the whole thing raised to n, dy dx would be, again, without actual numbers, you guys can use what I taught you to differentiate. The outside function is something raised to n, so it becomes n, f of x, keeping the inside function the same, raised to n minus 1, times the derivative of the inside function, which we denote as f prime of x. So this is just a general rule, isn't it? Yes, it's just a general rule the textbook explicitly states, but if you get the logic behind it, you don't need to know that. Let's say you have y is equals to f g of x. Again, this is just function notation. I don't know why they're putting this there to confuse us, but to do this, differentiate the outside one, keeping the inside the same, so that would be f prime g of x times the derivative of the inside function g of x, which is g prime of x. So yeah, this is it. You get the logic: outside, keeping the inside the same, and then inside, and then multiply. For P3 calculus, it will just be two, like a composite function made of two functions. It can get much more complex. It can become 3, 4, but that's not in P3 or P4 actually. Another example the textbook gives, I want to exhaust all the examples so that you guys have all the knowledge you need. So root of 5x squared plus 1. Write this as 5x squared plus 1 all raised to a half. Now, outside function again is power of half. Inside function is 5x squared plus 1. So dy dx is half. The whole, repeat the inside function as it is. Subtract 1 from the power. So that makes it negative a half, because half minus 1 is negative a half. Times the derivative of the inside function is 10x, because yeah, 10x. So this half times 10x gives 5x all into 5x squared plus 1, and that's a negative half. And yeah, that's all. That's the gradient function. Now when you plug in a value of x, it gives you the gradient of this graph at a certain value of x. That's what derivatives are by definition. Remember, that's why Newton invented calculus, so that he can calculate gradients of a graph at a certain point. Then another rule, this is again something that will be useful when you have functions written y is equals to f of x, then it's easy. Dy dx is just f prime of x. You just differentiate this thing turn by turn, the x terms. But let's say a function is written as x is a function of y. How would you do this? So for this, you would find dx dy, which would just be differentiating all these terms in this function. That would be using all the rules we have learned from now. So f prime of y, and then dy dx is just 1 over dx dy. So this is just a general rule you need to know. Dy dx is just 1 over the whole of dx dy. So that gives you dy dx, because that's what we're interested in. Dx dy gives the reciprocal of the gradient. But if you want the gradient function as it is, dy dx is 1 over dx dy. That's just a general case you need to know. They will test you on that in some places. So that's it for chain rule. Now we go to two more very important things. Product rule.